Go ahead.
Yeah. Hello. Good afternoon or good morning, everyone. I'm Prosper Dovonon from Concordia University, sitting in Montreal. So I would like to welcome you all for this presentation for the virtual time series seminar by Kenichi Nagasawa from University of Warwick. So he will be discussing optimal granular IV sequential estimation of long panel with finite cross-section. So I let it to Kenichi to present. Thank you.
Great. Yeah, thank you, Prosper, for the introduction, and thank you for to organizers, for organizing this, and then thank you for being here. And I'm very excited to present this work, which is about granular instrumental variables. And so, as the title says, and I just said that this is about granular instrumental variables, and the idea of granular instrumental variables is that we have the individual level shocks or disaggregated shocks, and we can use these as exogenous variation in aggregated endogenous variables. And so these individual level shocks or disaggregated shocks are not directly observed in the data. So we assume panel structures in the data, and exploiting this panel structure, we can extract idiosyncratic shocks. And these extracted idiosyncratic shocks can be used as instrumental variables to estimate structural equations or some causal effects. So this idea of granular instrumental variable (GIV) is useful in contexts where the instrumental variables are difficult to find, and also the context where the source of endogeneity can be captured by aggregate shocks. And I'll be more specific about what I mean by this in the next slide using an example. But before doing that, I want to emphasize that the type of setting that we are considering in this paper is the panel structure where the number of cross-sectional units is fixed and the time dimension going to infinity. So that's the type of setting that we are considering. So now I want to, kind of review the idea of granular instrumental variable using an example. So let's say that we are interested in, estimating some, a structural relationship, between some aggregate variables. So using this empirical example, the outcome of interest is a domestic output of a country, and so that's DT. And then on the right-hand side, you have the net capital inflow to a specific country. So here we are interested in the effect of capital inflow to the domestic output of that country. And here, this right-hand side variable B, net capital inflow, has this specific structure, which is weighted sum of disaggregated variable. So YJT, where J index denotes the locations across the world. So money or capital can come from different locations in the world, and so this J indexes different locations from which the capital is coming to this specific country. And the total capital inflow can be represented as the weighted sum of these different capital flows from different locations. So this specific structure of the aggregate endogenous variable being the weighted sum is quite important in this granular instrumental variable. So I wanted to emphasize that. And here Sj denotes the share of different locations in terms of the total capital inflow. And here so you have this simple linear equation, and you might be tempted to estimate this equation by just OLS, but here just running OLS might not give you consistent estimate of the parameter of interest, which is psi. So this measures the effect of net capital inflow to the domestic output, and OLS might not be consistently estimated parameter psi because of the possible endogeneity issue. So in this empirical context, the one source of endogeneity can be global financial conditions. So global financial conditions can affect the GDP of this specific country. So it's like a macroeconomic variables condition, and then the global financial condition can also affect the individual capital flows. And because this is global condition, it affects different locations in the world, and that affects each of the YJT. And because B, the right-hand side variable is a function of these disaggregated variables. That means that there's possible correlation between the BT and the structural error epsilon t. So that's a possible endogeneity issue, and there could be other factors that creating the endogeneity issue. So to tackle this endogeneity issue in the granular IV approach, we model the disaggregated variable, disaggregated capital flows using the interactive fixed effects. So here, YT, this is n times 1 vector. And then, we have this usual formulation of the interactive fixed effects model. And here, lambda is the n times R matrix of factor loadings. So here, R is the number of factors, and FT is the R times 1 vector. And so, this FT represents, common factors, that creates the endogeneity issue. So, global financial condition is one of the factors. And then, you can think of other, factors that are affecting the, all the locations in terms of the capital flow.
Just a quick question.
Yes.
Are those factors observed?
No, factors are not observed. So,
latent. Okay.
Yeah. So here, what is observed is the YT, the disaggregated variables. And so I'm going to say that, in the first part of the talk, lambda, the matrix of factor loadings, will be assumed to be known. And in the second part, we are going to discuss the case where you need to estimate lambda in the first stage. But for the first part, we're going to assume that lambda is known, but the factors are not unknown. Factors are not known. It's not observed. And so the important idea here is that the factors capture all the source of endogeneity, and this UT, which I'm going to call idiosyncratic shocks. So this UT is assumed to be orthogonal to the error in the structural equation. So the interpretation is that these UTs are shocks to each individual, but this has nothing to do with the aggregate level fluctuation. So this is just purely shocks to each individual. And so these are kind of orthogonal shocks. And so formally, what we assume is that conditional expectation of the structural error epsilon given UT is 0. So this is what I mean by the idiosyncratic shocks being orthogonal to the structural error. So having made this assumption, if you observe UT, then you can use that as an instrument because UT affects the disaggregated variables YT, and disaggregated capital flows in turn affects the this variable BT. So it satisfies the relevance condition, and the instrument exogeneity is assumed here, and and it's based on the idea that factors capture all the sources of endogeneity. So if you observe UT, you can use that as an instrument, but here you don't observe UT. And instead, what we do is to use the observed disaggregated variables to extract the idiosyncratic shocks. And so, as I already said, we assume the factor loadings are known. And if you know the factor loadings, lambda, then what you can do is to project disaggregated capitals onto the orthogonal complement of the span of lambda. So this M lambda matrix represents the projection matrix that projects random variable to the orthogonal complement of the span of lambda. So once you do that, this factor part disappears because it is spanned by this lambda. So M lambda YT equals to M lambda UT because you are removing the factor part. And because this M lambda YT is a function of idiosyncratic shocks, this remains as a valid instrumental variable. So this is a basic idea of granular instrumental variable. And here in the disaggregated capital flows, we can include covariates and also in the main equation. But here I'm omitting the covariates for simplicity, but you can add that in the actual application. So that's the kind of overview of the granular IV. And so this has been proposed in the literature. And so what we are going to do is to build on this idea and further refine the theory of econometric theory of granular IV. So in terms of the contribution, what we do in the paper, there are two things that we do. So the first thing is to construct optimal or efficient granular IV to estimate the structural parameter or the causal effects. So I just talked about the parameter of interest in the aggregated equation. So that's like a one setting where you apply granular IV, and there's also another setting where you want to estimate a structural parameter in disaggregated equations. And so I'm going to talk about these two cases and talk about how to construct efficient granular instrumental variable estimator. So that's the first part of the contribution. And here, for the first part, we assume that the factor loadings are known. And in the second part, we switch gear. And in the second part, we talk about the asymptotic distributional theory of the granular IV estimator when you don't know the factor loadings. So in the second part, we talk about unknown factor loadings lambda, and we need to estimate it in the first stage, and we discuss how does that affect the asymptotic variance of the granular IV estimator. So the two parts are a little bit different in the sense that in the first part we focus on the efficiency, and the second part is really about characterizing the asymptotic distribution theory. Okay, so before going to the details, I just want to mention some related literature. So
I have a quick question, if I may.
yes.
How to motivate the fact that this factor representation uh, like produces some idiosyncratic errors for you that is orthogonal to, like, that would be suitable instruments that is orthogonal
Okay. Yeah.
to epsilon. So
So
how do you
idea
motivate?
is so in this context, the idea is that the source of endogeneity is captured by these aggregate shocks. So like global financial conditions and other like world level macroeconomic shocks. So those are the source of endogeneity, and so this is really the idea of Gabay and Koijen, where they propose that these disaggregated shocks, we should be able to use it as an instrument because this is kind of random thing happening to each individual rather than it's affecting, so these individual shocks kind of propagate, to the economy because of the idea of granularity. But, if you go, if you trace the origin, these shocks are really, kind of random shocks. So, that's the kind of, main contribution done by Gabay and Koijen. As I was going to say, since the Gabay and Koijen proposed this idea of granular IV, there has been increasing number of literature where they apply this idea to identify structural parameters and causal effects. So I think we are really kind of building on this framework, and then we do further econometric theory on it. So I think the idea is really coming from this strand of literature to really exploit the idea of granularity to identify some causal effects or structural parameters.
But so then, because you have on with like you have more many components, if the size of psi is small enough, then you may be able to test if there is exogeneity in the end. Is it possible at all that this can be done? And then you may be able to know at least empirically that this idea survives to the GMM over identification test, for example.
Yeah, I think that's a very good question, but I think it's sort of not directly related to what we do in this paper. So let me postpone the discussion until the end so that we can have
Okay,
discussion. Yeah.
okay. Thank you.
Thank you. Thank you for the question. So I already said that Gabay and Koijen started this literature, which is growing in recent empirical literature, and there are also several papers that look at the econometric theory aspect of the granular IV, and I just listed three papers here. Banafti and Lee consider the large panel settings where the number of cross-sectional units also going to infinity, and there are theoretical challenges in that setting. And also Baumeister and Hamilton, consider the maximum likelihood estimators to really, get efficient estimator because these estimates tend to be, quite noisy. So they really exploit that, additional structure to get, really efficient estimators. And Kian consider extension of granular IB framework where the paper allows for the flexible form of heterogeneity in slope coefficients. And we add to this literature by developing further econometric theory of granular IV. So now I'm going to talk about the construction of efficient granular IV in the aggregated equation. So I already talked about the example where I wanted to estimate the effect of capital inflow to the on the domestic output, and so we already talked about this assumption here, which is the UT really is an idiosyncratic shock, and we also make this assumption that structural error has conditional homoscedasticity, and this simplifies the formula of the optimal instrument. And so having assuming this condition of the idiosyncratic shock, we can rewrite the GMM moment condition. So if you pick the right parameter psi, this difference will be the epsilon, and so it will be conditionally mean zero because the m lambda yt is a function of ut. So this is the moment condition that we start with. And so having this conditional moment restriction, we can characterize the optimal instrument or the optimal GMM estimator by looking at the optimal instrument. So having assumed this conditional homoscedasticity assumption, the optimal instrument is given by the derivative of the moment condition with respect to the parameter of interest. So the derivative equals this one, the second term here, and this BT, the aggregated capital inflow, is a weighted sum of the disaggregated capital flow. So here S is a vector of share or the weight, and YT is the vector of disaggregated capital flows. So BT by definition equals this S prime YT, and so I just have this form here. So this is the optimal instrument. So just for the sake of I guess reviewing, I mean if you have studied GMM for a while, so this is general optimal instrument in the conditional moment restriction. So if you have this moment condition, where m is the moment function and z is the a conditioning variable, then if you have this conditional moment restriction, then this unconditional moment holds because so where unconditional moment is created by having this vector of instruments, which is function of this conditioning variable z, and from the theory of GMM, it has been well established that if you pick this b in a specific way, then you can get the most efficient GMM estimator, where you pick this b to be this formula here, which is a product of the derivative of the moment function and the conditional expectation and the conditional variance of the moment function. So in our context, we assumed the conditional homoscedasticity. So this term will be just constant, and we just have this term for the optimal instrument. So it was just a reminder for those of you who haven't studied GMM for a while. Okay, so that's where this formula of the optimal instrument comes from. And so having characterized the optimal instrument, you can formulate the most efficient GMM estimator using this optimal moment condition. So maybe I should say that because so the class of estimators that we are thinking about is this GMM estimator, and the type of dependent structure we are imposing on the data is martingale difference. If you have a serial correlation, the form of optimal estimator changes. So we are considering this class of estimators. Okay, so this is like a new result, and I think nice thing about this result is that we can make a nice connection back to the original contribution by Gabay and Koijin. So to explain the connection between our result and the original result, I'm going to decompose this disaggregated capital flows into two parts. The first part is this projection onto the orthogonal complement of span of lambda, and the other part is the projection onto the span of lambda. So this is just a algebraic identity. And having made this decomposition, if we go back to our optimal instrument, this one on the left-hand side, you get the first part, which is just the share weighted sum of the m lambda yt, because you condition on m lambda yt, so this just comes out of the conditional expectation, and the other part is the conditional expectation of p lambda yt given the m lambda yt. So this first part of the decomposition, which is highlighted in red, this IV exactly corresponds to the GIB proposed by Gawai and Koijen. So in their paper, they talk about the optimality of this instrument of this IV in a class of IV estimators. And so here, what we are doing is that we look at a larger class of estimators, and we characterize the optimal estimator within that class. And so if the conditional expectation equals linear projection, let's say you have joint normality of the underlying shocks, then this conditional expectation equals the first term. So, the conditional expectation being, equal to the linear projection. So in that special case, our optimal instrument coincides with the, instrument proposed by Gawai and Koijen. So in that case, the two results are the same. But if you are outside of this special case, then there's a potential efficiency gain by including the second term of the what we characterize as the optimal instrument. So if you just apply the IV of Gawai and Koijen, you're potentially leaving some efficiency gain on the table. So that's the main finding of our the first main finding of our paper. But I should also make a remark, which is that this first part, what we call linear instrument. So this linear instrument is nice in the sense that once you know lambda, the factor loadings, then you can just calculate it from the data. Whereas this nonlinear part of the instrument, you need to estimate the conditional expectation. So there's additional step that you need to do before you can implement this optimal instrument. So there's that trade-off. And so this is work in progress. So we are currently working on to analyze this nonlinear term more. But for this talk, in the remainder, I'm mainly focusing on this linear instrument. Okay, so that's the first part. And now I want to talk about efficient GIB in what I call disaggregated equation. So there's another set where you can use granular instrumental variables. Okay, so to explain that, let me use the supply and demand example. So first, I have the aggregate demand equation, and it could be supply equation, but I just focus on demand for concreteness. So let's say I have this aggregate demand equation where, and this is really the inverse demand function, where you have price or log price on the left-hand side, and on the right-hand side, you have the equilibrium quantity, where you can think of equilibrium quantity as the market share weighted individual supply. So here ZJT is the individual supply, and SJ is the market share of cross-sectional unit J. And then so this is the aggregate demand, aggregated equation. And then I have the individual supply equation or disaggregated equations. And so for each individual supply, we model it using the interactive fixed effect. But importantly, we have this endogenous variable on the right-hand side, which is price or the log price. And so, if we write it in a vector form, so this ZT is n times 1 vector, and we can write it in this way, where the second part has the interactive fixed effect structure as we did in the previous section, but we also have this additional part, which is the price or the endogenous variable. And here, iota just means the vector of ones, n times 1 in vector of ones. So to map it to the previous notation where I used YT for the disaggregated variables, we can map that to the notation by having by considering the difference between the individual supply minus this phi times the price. Okay, and then without loss of generality, without loss of generality, we can always include time fixed effects in the disaggregated equation, which means that first column of the factor loadings will be just 1. So if you have just 1 in the first column, then the corresponding factor you can interpret it as time fixed effects because it affects all the units in the same manner. So having included time effects, when you project out the disaggregated variables onto the orthogonal complement of the span of lambda, this m lambda zt equals to m lambda yt because this first part of the yt will be removed by projecting onto the orthogonal complement of lambda. So even though the setup in this case is slightly different from what I talked about in the previous part, actually when it comes to the construction of the granular IV, the difference doesn't matter. When you compute this m lambda zt, it is m lambda ut. So it's still a function of the idiosyncratic shocks. So the same argument goes through as in the last section. So optimal instrument for the parameter psi, which is the demand elasticity, the optimal instrument is still the same form where I just replace yt with zt, but it's really the same thing. Okay, so this is what I already talked about before, but now there's additional equation that we want to estimate, additional parameter that we want to estimate, which is this phi parameter in the disaggregated equation or in the supply equation. So this is supply elasticity. And importantly, we are assuming homogeneity of the supply elasticity here. And so, and I think the natural thing to, ask is, can we use the same instrument to estimate the supply elasticity? And you need a little bit more, you need to, be careful because the error term in the supply equation contains the UT, and that's you use to construct the instrument. So if you don't do, if you are not clever, if you don't change the equation in a clever way, this error term UT is going to be correlated with IV. So this, IV doesn't work, as is. So you need to do something else. Okay, so then I'm going to talk about how to solve this, issue of estimating the, supply elasticity phi. So first thing that I want to say is that, we're going to make this additional assumption. The factor is orthogonal or orthogonal to the idiosyncratic shocks. And the idea is, how I motivated, orthogonality between the structural error epsilon and the UT. And because FT captures the source of endogeneity, for UT to be valid instrument, it should be really orthogonal, to these factors. So, this assumption is like a natural extension of what we already assumed. And so, this one I think, is fine. But even if you assume this part, the orthogonality of factor to the idiosyncratic shocks, you still have the issue that this UT shows up in the error term of the supply equation. So what we do here is that let's say H is a vector of weights, it's n times 1 vector, and we want to find weights such that when we weight these disaggregated variables, disaggregated supplies, so we want to weight supplies in a way that we can still use the granular instrumental variables. So so first let me define some notations. So H again is a vector, and we just fix a scale of this vector H. So we just assume that the sum of these elements of H adds up to 1, and then we think of this weighted disaggregated supply ZHT, which is just H weighted disaggregated supply, and using the this formulation, the interactive fixed effect formulation, we can see that this ZHT, the H weighted disaggregated supply, takes this form, where the first part is just phi times PT, and the rest is weighted by the vector H. And now so the question is, so this is the instrument, the granular instrument, m lambda ut or m lambda zt, it's the same thing. So this is the granular instrumental variables, and the question is, can we pick H such that this unconditional moment holds? And if this unconditional moment holds, then we can use this moment to estimate the supply elasticity. So the question is, is there such weight vector h that satisfies this moment condition? So using this part, and if we pick the right phi, the true phi, then we have these remaining error terms here, and the factors are orthogonal to the u. So we can so this part will be 0. I mean, when you compute the expectation. So really, what's remain is here the weighted sum of the idiosyncratic shocks. So this left hand side equals to this one here, and then we just use some notation, which is the covariance matrix of idiosyncratic shocks. We just write it as omega. So this moment condition holds if and only if this condition holds, where m lambda is given because we know what lambda is, and omega is a covariance matrix of the idiosyncratic shocks, and h is something that we want to pick. And so to phrase it in another way, this unconditional moment condition holds if and only if the covariance matrix of idiosyncratic shocks multiplied by this wave vector h lies in the span of the factor loadings, because this m lambda is orthogonal to the span of lambda. Or to also, even put it in another way, the h vector, the weight vector, should be in this form where omega inverse is the inverse of the covariance matrix of the idiosyncratic shocks, and lambda is the factor loadings, and gamma is just some vector. So this is like the parameter you can choose to create different h vector that satisfies this unconditional moment. So this is another finding of our paper where we show that there's a range of weight vector h that you can choose to satisfy this moment condition to estimate the parameter in disaggregated equations. And so, okay, so to be fair, this is not completely new in the sense that Gabay and Koijen already showed that there is a vector h that you can use to estimate parameter in disaggregated equations. And they specifically show that this h vector, so elements of h, is proportional to the variance of the jth units idiosyncratic shock. And so they assume uncorrelatedness, but I guess the specific details doesn't matter. What is important is that Gabay and Koijen already show that there exists such h. And what we show is that beyond what Gabay and Koijen show, there are other possible choices of weights that you can use to estimate parameter in disaggregated equation. And in particular, so we just show that this h vector works for the purpose of creating the valid moment condition. And if you pick this gamma to be a specific choice, then this h vector corresponds to the choice of Gabay and Koijen. So we have a kind of general result which specializes to the Gabay and Koijen's case.
Yeah, just a quick question. So
Yes, go ahead.
If I understand well, in the process, h will be estimated as well.
So h is something that you need to pick, and of course it can be estimated in a way, because so if you don't know what gamma is and if you don't know what omega is, I think you can. So I think it's like a two-step GMM where you have the consistent estimator first, and then you can iterate. Even though we haven't got that far yet, here we just characterize what h is valid. But I think that's a good point, and then hearing that question made me think about this multi-step estimator, but we haven't done that yet. So here what we have is just characterization in the population.
Okay.
Yeah, thank you. Okay, so what I was going to say was, given our result, I think the natural question is, because there are multiple choices of valid h, what is an optimal h? I mean, is there a choice of h that makes the granular instrumental variables asymptotically efficient? So that's like a natural question. And also another question is that does the choice of h affect the form of the optimal instruments? So now I'm going to talk about these two questions. And so the way I do it is, first I'm going to fix h. Suppose that I have a valid weight vector h, and then we want to characterize the optimal instruments based given the h. And then given the optimal instruments, we want to minimize the asymptotic variance of the GIV estimator. So as I said, I'm going to first start with fixed H and assume that this H is valid, and then we want to characterize the optimal instrument. And to characterize the optimal instrument, I actually need to strengthen the condition. So before, I talked about the valid H where this unconditional moment is true. But to characterize the optimal instrument, I need conditional moment restriction. So I'm going to assume that this conditional moment restriction is true. So this is stronger than what we had before. And also, I'm going to assume that conditional homoscedasticity is true given H. And so these assumptions can be possibly justified if the idiosyncratic shocks are jointly normal. So if idiosyncratic shocks are jointly normal, unconditional moment restriction implies this one, and also normality implies the homoscedasticity. Okay, so having assumed this condition, we can characterize the optimal instrument by looking at the Jacobian. And so by taking derivative, we get this term. And using the moment condition from the demand elasticity, the price equals to price equals to demand elasticity times the share weighted disaggregated supply. So we obtain this formula, and because the scaling doesn't matter for the optimal instrument, we see that optimal instrument for the supply elasticity coincides with the optimal instrument for the demand elasticity, although we did assume stronger conditions. And so that's a new finding. We characterize the optimal instrument for the disaggregated equation, and as it turns out, this optimal instrument does not depend on the weight vector H. And this is nice, but it doesn't mean that choice of H doesn't matter for the asymptotic variance of the GIV estimator, because optimal instrument doesn't depend on H, but the asymptotic variance of GIV estimator can still depend on H, and actually it does depend on H. So, so this is the first part. So whatever the H you choose, the optimal instrument takes the same form. So that makes the analysis a little bit easier. And so again, with normality, we have we just have the linear part of the instrument. So, using this linear instrument, we can characterize. So having characterized the optimal instrument given H, the moment condition, we can use this one. And then we can characterize the asymptotic variance of GMM estimator of the supply elasticity under regularity conditions. And the asymptotic variance looks like this, where the Jacobian doesn't depend on H, but this kind of mid part of the GMM asymptotic variance formula does depend on H. So optimal choice of weight vector H can be characterized as a solution to this minimization problem, where you have the expectation of the square of this instrument and the square of this difference, and and then there's a restriction on H such that H has to satisfy this form. So having put it in this way, we can interpret an optimal H to be a solution to this constraint weighted least square of projecting price onto the disaggregated supply divided by this supply elasticity. So we don't have. This is the result we have, and so looking at this, we see that in some cases the choice of H vector proposed by Gavin and Koije might not be the optimal one. So there is some room for improvement in terms of the efficiency of the granular instrumental variable estimator, and then I'm going to demonstrate using a empirical illustration later. So this is our second result, where we characterize how to make the granular instrumental variable efficient for the disaggregated equations. Okay, so that was the first part of the paper, and so up to now we have assumed the factor loadings lambda is known. So we just use known factor loadings to characterize the most efficient estimator. And now I'm going to switch gear, and then I'm going to think about the asymptotic distribution of granular instrumental variable when the factor loadings are unknown. So the factor loadings needs to be estimated in the first step. So given a factor loadings lambda, you can write the sample GMM moment condition in this way in the first equation, where I'm looking at the aggregate demand equation. So I want to estimate this parameter from the aggregated equation. So given lambda, I just solved this GMM sample moment condition, and because psi is a scalar, I can have a closed form solution. But the lambda is not known in this setting, so we need to estimate it in the first stage. And to talk about the estimation of lambda, it is convenient to rewrite this sample moment condition. And so lambda, the first column is just vector of ones, iota, and from column 2 to column r, these are the factor loadings that you need to estimate, which I write as lambda check here. And without loss of generality, the columns of lambda can be made orthogonal. And so once we make the columns of lambda orthogonal, then I can rewrite this sample moment condition in the second equation, where I first orthogonalize the disaggregated variable z to the orthogonal complement of this vector of ones, so which is done by this d mean matrix dn. And then after that, I can do the projection onto the orthogonal complement for the remaining columns of lambda, which is represented by m lambda check. And so this is really equivalent sample moment condition, but this is more convenient for our purpose because now we can single out the columns of lambda which we need to estimate in the first stage. And so under regularity conditions, we can establish this asymptotic expansion of the granular instrumental variable estimator psi in this way, where there are two parts of the asymptotic expansion. The first part is this sample mean, where if you know lambda exactly, this will be the influence function of the asymptotic. This will be the influence function of the granular instrumental variables. And there's a second part which comes from the factor you estimated columns of lambda. So if you can characterize the influence function of the factor loading estimator, then you can completely characterize the influence function of these granular instrumental variables. So now I want to make a remark, which is, as I already said, the first stage estimation of the factor loading affects the asymptotic variance. But on the surface, this seems to be different from the standard optimal instrument estimation in the GMM settings, where estimation of the optimal instrument does not affect the asymptotic variance, at least to the first order. And here it seems like estimation of the instrument does affect the asymptotic variance. And to explain this difference, I want to highlight that in standard settings, the conditional moment restriction is with respect to a fixed sigma field, meaning that you have some variable z, and then conditional moment is with respect to the sigma field generated by this random vector z. But in our setting, the sigma field is generated by m lambda zt, where lambda has to be estimated in the first step. So the sigma field in our context has a nuisance parameter, and this creates a difference in terms of the how the first stage estimate affects the asymptotic variance. So I just wanted to make this remark because when we first worked out this result, we had this question of why is it different from the standard optimal IV setting. So it's not the same setting actually. Yeah, that's why. Yeah. Sorry.
I have a question that may not be that important, but out of curiosity, if it happens that lambda has so many columns that m lambda times z doesn't have materially enough dimension to identify your model, is this something that can happen?
Yes. So yeah, I skipped the discussion because it has been discussed a lot in the literature. But yeah, you're right. So let me see. So Yes, definitely. So I think the important point is that if S belongs to the span of lambda, then this S prime M lambda is going to be 0. So in that case, your instrument is not relevant. So I don't know if that was your question, but there are conditions that we need to,
like at the limit.
there are conditions that we need to impose on the DGP that guarantees the relevance of the granular IB variable. And
Okay.
yeah, so maybe I should have discussed it in the introduction, but that has been pointed out by Gawai and Koijen. So that's the kind of terminology of the granular instrument. Granularity comes from where the weight vector should not be uniform, because if it is uniform, it belongs to the span of the factor loadings, because the first column of factor loadings is vector of ones. But yeah, thank you for the question. Okay, so what I was saying was, this is different from the standard, conditional moment restriction model because of the sigma field containing the nuisance parameters. Okay, so what we do in the paper is to look at the some estimators of the factor loadings and characterize the asymptotic distribution of the granular instrumental variables when the factor loadings are not known. And when you estimate factor loadings, as is well known in the literature, you cannot separately identify the factors and the factor loadings. So you need to fix the rotation. And so here we are fixing rotation by assuming that covariance matrix of the factors are identity matrix. And then we can do this demeaning to isolate just the lambda check from the entire lambda matrix. And so we have this interactive fixed effects model doing demeaning. And now I want to talk about, briefly talk about the GMM approach proposed by Gawai and Koijen, where they define this object FTL. So L is a candidate of lambda check. So this is like the parameter that you want to estimate. And given lambda check, the candidate of lambda check, you can formulate this FTL, which is really the OLS estimate of factors given thinking of this lambda as regressors. So Gawai and Koijen formulated GMM moment using that. If you plug in the true lambda check into L, and that will be kind of estimated factors, and so this one will be just the error term here in the regression, and error term in the regression should be orthogonal to the factors. And using this intuition, they formulated this GMM moment condition to estimate lambda check, where you pick the appropriate lambda L to minimize this GMM moment condition. But this has some issues we noticed, which is that if you take the population moment, so you just take the expectation of this data, and if you assume homoscedasticity of the idiosyncratic shocks, the population moment equals to 0 equals to this right-hand side object. And so again, L is the parameter that you are trying to choose to make this moment condition hold. So if you pick lambda to be lambda check, clearly this moment condition is satisfied because M lambda check will be orthogonal to lambda check, so you have 0 here. But if the number of cross-sectional units is larger, large enough that compared to the number of factors R, then you can also choose this L, the columns of L, to be columns in the orthogonal complement of span of lambda check. And if you do that, then this part will be 0. So you can see that there does not exist unique L that satisfy this population moment condition, but there are other L's that make this population moment condition true. So it violates one of the assumptions for the GMM asymptotic theory. So our suggestion is to use different moment to estimate the factor loadings. So here we use this specific moment, and this is not our invention. This has been in the literature. But nice thing about this moment condition is that you can also estimate the covariance matrix of idiosyncratic shocks. Of course, you need to put some restrictions, like you cannot allow for arbitrarily correlated idiosyncratic shocks across units. So one restriction is that you assume diagonality of this covariance matrix, which allows for the different variance across units, but you are not allowing for the correlation across units. But the point is that under this moment, you can estimate the lambda check and then also the covariance matrix of idiosyncratic shocks. And one tricky thing about this GMM moment condition is that the parameter, the factor loadings, lives in the the parameter space is a smooth manifold. It's not a vector space, so you need to take care of the theoretical challenge. But we do that in the paper, and we characterize the influence function of the GMM estimator. And I'm not showing the formula because I didn't find it super insightful just looking at the formula, but it's in our paper, and which we are hoping to make it public relatively soon, but we don't have it yet available yet. Anyway, so having characterized the influence function of the GMM estimator, we can plug that formula into here to characterize the influence function of the granular instrumental variables. An alternative to the GMM approach is to use PCA to estimate the factor loadings. But because we are considering the settings where the number of cross-sectional units is fixed, for the PCA to be valid, you need a homoscedasticity assumption on the covariance matrix of the idiosyncratic shock. So that's a drawback. But I think PCA is easier to use, or PCA is easier to estimate. So that could be a potential advantage. Okay, so that was the second part of our contribution, characterizing the asymptotic distribution of the two-step GIB estimator. And now we want to illustrate our theory using some empirical empirical example. So we look at the global oil market, and we build on the analysis done by Baumeister and Hamilton. So we have the monthly data on oil production for 5 countries plus rest of the world. So the number of cross-section units is 6, and the time period goes from 1973 to this year May, and we exclude period of COVID pandemic. So we have the time periods of 580, and we have disaggregated supply equations and also the aggregated consumption equation. And for this illustration, I'm going to focus on the supply elasticity, which is the disaggregated equation, where I want to estimate the supply elasticity parameter phi. And I hope you remember from the several slides before, to estimate this parameter in the disaggregated equations, you need to choose the valid wave vector h, and that can also affect the asymptotic efficiency of this estimator. And another issue that I want to mention is the choose number of factors R here. So as we see in the next slide, this number of factors is quite important for the estimate of the supply elasticity. So here I have the estimation results. So first, on the left column, I have the R equals 1, meaning that I just have time fixed effects to estimate the supply elasticity. So as you can see, you get negative estimate, which is not, which doesn't make sense. So the interpretation of this result is that you are not including enough number of factors to control to address the endogeneity issue. So probably only including time fixed effects doesn't do in this specific empirical application. So we looked at the the eigenvalues when we estimate the factor loadings, and by looking at the sequence, what's the word? I mean, we look at the like a neighboring eigenvalues, and R5 seems to be a reasonable choice. So we include the 5 factors, and that at least put the point estimate to a reasonable range, but it's still quite noisy estimate. So when you look at the confidence interval, the confidence interval still includes the negative value, so which is a bit worrying. So next, what we do is that keeping the number of factors, we change the vector h, and the way we choose the vector h is to use this choice, where we are using the estimated factor loadings and combine them to create the theoretically at least asymptotically valid choice of vector weight, and then that reduces standard error quite a bit. So I think this is along with a line of our theoretical findings where the choice of H can be quite important for the efficiency gain for the granular instrumental variables. So I think this is a nice illustration. Okay, so that was all for what I have. And so I mean, in this paper, we further developed the theory of granular instrumental variables, and we highlight the connection between our work and the original work done by Gabay and Koijen. And so that was the efficiency part where we assume the factor loadings to be known. In the second part, we analyze the asymptotic distribution of the two-step GIB estimator, where we need to estimate the factor loadings in the first stage. So that's it. Thank you so much for your attention.
Okay, thank you, Kenichi, for a very nice, clear presentation.